All right, we're gonna get started, guys. So John couldn't be here today, but he wanted me to remind you guys that the dispenser design has changed. So if you're unaware of that, not from yesterday, it's the same as yesterday, but like from our first design, it's changed. So just if you're not aware that that happened, just reread the manual. So today we have a pretty great lecture for you guys. It's all of autonomy basically in a nutshell. Because the main challenge of MASLAB this year is the fact that we aren't giving you a map of the field now or ever. You're not going to know what the field looks like till the day of competition. So the question becomes, how do you get your robot to understand where it is in an unknown environment? And this is a really non-trivial task, but hopefully after today you'll have a general idea of how to do this. The first thing we're going to go through though is the sensor that we're giving you, which is new to, oh wait, we're using this now. Okay. Does this work? It does work. Oh yeah, before we get to that, it's always great when like, I mean, this is my first time TAing anything, but it's always great when you realize in the middle of lecture that people are actually learning something. So this is Eric's command line lecture yesterday. We put up the IP address and the password to the NUC that Eric was using, and someone SSH'd into our NUC during the lecture and replaced the MASLAB logo with a chicken picture. So thanks for that. That was fun. Yeah. So the first thing we're going to go through is LiDAR. What is LiDAR and why you care about LiDAR and why it's like the greatest thing since things were things. So a LiDAR, you're going to find a LiDAR in your kit we gave you from MASLAB. And a LiDAR stands for light detection and ranging, and that's a really fancy way of saying it's a 360-degree distance sensor. All a LiDAR really does is, so actually first let's talk about what a time of flight distance sensor is. And a time of flight distance sensor, basically what one of these things does is, this is what a distance sensor, time of flight distance sensor looks like. There's a transmitter and a receiver, and here's a wall. The transmitter is going to send out some known wavelength of whatever, sound, light, whatever it happens to be. Ultrasound runs on sound. LiDAR runs on light. And it knows the speed of this wave. So it knows that's called C equals speed. And the transmitter is going to transmit a beam. It's going to hit the wall. Actually, the moment the transmitter starts transmitting, it's going to start a timer, t equals 0. It's going to transmit the beam is going to hit the wall. The beam is going to bounce back, and as soon as the receiver receives the light, it's going to stop the timer, and you have it's going to measure the amount of time it takes for this wave to go back, hit the wall, and come back, sorry. And based on that, since you know the speed of the light, or the wave, or whatever you've transmitted, you can then figure out the distance you are from a wall. And that's what a time of flight distance sensor is. We have a bunch. A lot of them use infrared. You'll see the ones in the lab upstairs are infrared. Ultrasound sensors work exactly the same way. LiDAR is a little bit different though. So the problem with a traditional time of flight distance sensor, if we look at an ultrasound sensor, is the fact when this beam transmits, the beam actually looks like your normal wave propagation. It goes out in like a traditional wave propagation kind of fashion. So like when this beam hits the wall, it could be hitting here. You really have no idea. So these ultrasound sensors are great for like if I just want to know how far I am from like a wall in front of me, and I know that wall happens to be flat. It's not great if I want to figure out what my environment looks like. So LiDAR solves this by using laser. And laser is a very focused beam of light, as I'm sure many of you are aware. So what a LiDAR does A LiDAR has, again, sensor, transmitter receiver, and it sends out a direct pointed beam, and it receives this direct pointed beam back. And then it measures the distance to this specific point over here. But a LiDAR also spins around 360 degrees. So you're going to, as the LiDAR spins, you're going to get a point here, 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 and you're going to get the R, the distance, R, and then the angle theta, at which it measured that distance. Theta equals 0 is the front of the LiDAR. So what this means is, let's say, I'm running out of whiteboards. Let's say I have a room that looks like this. I put a LiDAR here, and that's the front of my LiDAR. What I get out of this through, well, the first thing that happens is this LiDAR is going to spin around, it's going to measure its points, it's going to send all of this through a binary stream to your computer. You don't need to worry about the binary stream because all of the LiDAR drivers that come with the LiDAR takes this binary stream and converts it into something usable. This usable thing it converts it into is called a point cloud. And a LiDAR point cloud, depending on what's called the resolution of the LiDAR, meaning resolution meaning how finely grained the scan ends up being, how many points you get out of the scan. It looks something like this. So if this LiDAR were to spin around, I would set the center here of the scan. The origin of the scan is the location of the LiDAR. That's the origin. My positive x-axis, positive x, I think it's positive x-axis goes in the direction of the front of the LiDAR. My y-axis goes perpendicularly up because z comes out of the page towards me. And my point cloud looks something like this. Now that's a very low resolution point cloud because I don't want to draw 1,000 points. But this is what you tend to get out of a LiDAR. And how this is usually stored in a computer is they usually will give you a list of like, I think it's like theta R tuples. Because at this theta, you're at this distance R, at this theta, you're at this distance R, at this theta, you're at this distance R, so on and so on and so on, and that's what a point cloud looks like. And now this is really cool, and the reason this is really cool is because what this allows us to do is figure out with one sensor what our entire environment around us looks like. Because the problem with unknown environments is that the robot has no idea what the environment looks like, and therefore doesn't know what to expect or how to like localize in it if it doesn't know what the environment looks like, right? Because localization requires you to understand your environment. So what a LiDAR is one of the sensors that allows us to figure out what the environment looks like. There's many types of sensors out there. You can use 3D stereo vision cameras and those kind of sensors, but LiDAR has recently become pretty cheap. Like the LiDAR in your kit is about $100 and you can get a relatively decent point cloud out of it. And yeah, so that's kind of how LiDAR works. Is everyone following me on why? Okay. Where's the Xbox controller? Okay, here we go. This is our clicker today. Okay, yes. Yes, LiDAR is literally a time of flight distance sensor that spins. There's really not much more to it than that. The only distinction I'm gonna make is instead of getting like one value out of it, you get this point cloud. And depending on the number of channels your LiDAR has, channels meaning the number of lasers it has on it. Some LiDARs have up to like 16 lasers. The one you have has one. So you have a one-channel LiDAR. The 16-channel LiDARs give you like hundreds and thousands of points per scan. Depending on the detail of the point cloud, you can get different things. So the LiDAR you have will probably let you figure out where the walls are. 16-channel, like Velodyne LiDARs, can probably tell you there's a table in front of you, and like there's a chair, and a person just walked into the room, and so on. Yeah. Okay. Yes, LiDAR is great. All of current autonomy works on LiDAR for the most part. So self-driving cars, the immediate mapping of the surroundings works on LiDAR. The new robot vacuum cleaner is not Roombas, but there's a competing company called Neato. Neato vacuum cleaners actually have LiDAR, and they run the algorithm we're about to talk about in like 3 minutes. Maybe not 3 minutes, but soon. Yes, and this is a super detailed LiDAR point cloud. So you'll probably see the LiDAR point clouds that you're going to get look something like this with some more points. But this, I believe this is from a Velodyne 128 channel LiDAR, which means there's 128 lasers on this LiDAR sampling at like something like 1,000 hertz. So this is a ridiculous point cloud. And they were using, this came from a drone. They pointed the LiDAR downwards to map the terrain of certain area. But anyway, you get the idea. Yes. So now we've given you quite a problem. And the problem we have given you is that neither you nor your robot has any idea what your field looks like, right? And on top of this, you need to somehow figure out how to localize your robot, meaning figure out where your robot is within this environment that you've never seen before. And then after that, you need to plan a path to get to certain points. And you don't even know where those things are in your field, right? So it's a non-trivial task. But it comes down to two individual problems. I'm going to go through these two problems first on their own before we can figure out how to solve them together, because if you don't understand how each of these work, you aren't going to understand how both of them can come together to solve this problem. So the two main problems here are localization, figuring out where you are, and mapping, figuring out what your environment looks like, right? What's my next slide? Okay, wait, we'll get to that. Okay. So the first thing I want to talk about is localization. So localization is when, like, let's say this is the shape of the room you've been given. Like you know that's what the room looks like. This is a map. Your robot has this map. It is very well aware of this map. It knows what the distances here are. It knows what the shape is. It knows its environment. So now let's say I get a LiDAR scan. What's the best way to do this? This is my known map. Let's say my robot is another color. Let's say my robot is here. And it is facing this way. I'm now going to get a LiDAR point cloud. My point cloud is going to look like this. Something like that, right? Here is the robot. So this is 0, 0. This is my x-axis. This is my y-axis, right? Yeah.
So for that kind of square angle there that you've got,
square angle,
or like the right angle there, like it won't like get into that corner there. So what will you actually see?
This corner?
No, the other one right next to it. Yeah, that one. Like the laser won't be able to bend around that.
Yeah, you're right. In this case, like your point cloud would actually. So the point he's making is because of where the LiDAR is currently station, like the beams won't actually be able to hit this corner and read it. For argument's sake, let's pretend it can for right now. But what it would actually look like is something like that. And this part of the point cloud would just be like missing. Good point. Let's ignore that for now. It turns out that's not going to matter later either. But just for the sake of understanding localization, let's say we get this as our point cloud. And this is my origin point cloud. And let's say my map origin, let's put that arbitrarily here. It really doesn't matter what the map origin is, because what localization is going to try to do now, again, this is one type of localization. This is called LiDAR-based localization in a known environment. What we're going to now try to do is take this point cloud, and we're going to try to match it to our map. This is called scan matching localization. So basically, at the highest level possible, what this algorithm is going to do is say like, oh look, I have a wall here, high wall. That wall kind of looks like this wall. That wall kind of looks like this wall. Oh, that one kind of looks like this one, and that one, and that one, and that one, and that one. Basically what it's going to do is do a bunch of rotations and transformations from this origin on this map to figure out how do I match him to him, right? It's just going to... There are many ways to do it. Linear regression is actually one of the most common ways, or sorry, not linear regression. First it takes, we'll go through the details of how you actually get landmarks out of a scan in a couple slides. But basically it's going to just take like least squared error between these two scans to figure out how to match them. And then what it's going to notice is, okay, this was my origin. I've matched the scans. This is the origin of the scan, which means with reference to this 0, 0 origin of the map, this is where my robot is. And that's localization. So localization in one sentence is, I know what my environment looks like, but I don't know where I am. So this is one of the ways you figure out where you are. Mapping is a little different. And mapping is when you know where you are in the environment, but you have no idea what your environment looks like. And that sounds really weird when you first say it, because you're like, how the heck could I know where I am if I don't know what my environment looks like? But it's funny because you have a device probably in your hand that does this every single day. GPS. GPS has no idea what the Earth looks like. So this is the Earth. It's kind of flat over here and not very detailed. But so I honestly drew this with no details in it to make a point. GPS has no idea what the Earth looks like. GPS knows, I don't know what the origin of GPS is. I'm just going to assume it's the North Pole over here. GPS knows the location of, actually no, sorry. NASA is here somewhere. That's Florida. GPS satellites, we're going to put satellite here, a satellite here, a satellite here, a satellite here. GPS knows basically two things. Number one, that the Earth is round. And number two, NASA is there. And GPS says, okay, I know my R, theta, Z, I don't know, some spherical coordinate system. It knows where it is in reference to NASA. All these satellites know where they are in reference to NASA. And then you are swimming across the Atlantic Ocean somewhere here. And now all these GPS satellites are like, okay, well, I know where you are in reference to the satellites. So that means, with some math that we don't care about, I know where you are with reference to NASA. and let's say NASA is the origin of the whole world, I know where everything in the world is with reference to NASA, so I know where everything is with reference to each other. This is how GPS works. It has no idea that you're in the middle of the ocean. It has no idea NASA is on Florida. It has no idea what Florida is. It just cares that it knows where its origin is, whether I set that as NASA, the North Pole, the South Pole, Russia, like, it doesn't matter. It can still do the math, right? Because it doesn't care what the Earth looks like. It knows where you are with reference to this weird spherical blob it doesn't understand. This is step one to mapping. This is how you know where you are in a global coordinate system, but you have no idea what this system looks like. So it is this. The reason I'm going through this is I'm trying to point out that it is possible to know where you are without knowing what your environment looks like. So mapping has turned. So the fact that this is possible has turned into quite a lucrative industry. Talk to any urban planner you know. This makes money. So then mapping is the art of understanding when you know where you are, but you don't know what your environment looks like. What happens is, let's say this is a section of the Earth. In this case, it's a cube. What color do I want to use? Purple. I'm going to use purple. Let's talk about drone mapping. Drone mapping is become pretty common in industry today. It's actually one of the most common ways we now map the Earth's surface. And the reason this is possible is because of GPS. So I have a drone. There's no way I'm going to be able to draw this. Okay, this is a drone. So that drone knows its position on the Earth. And thanks to new fancy RTK systems, which stands for real-time kinematics, which combines both satellite and actually cell phone towers now to figure out where your drone is on the Earth, it has about 1 centimeter precision in the measurement. What it's going to do is say, like, okay, I know where I am in the world. I'm going to take a picture. I'm going to take a picture of that square over here. So now I know that at this specific coordinate on the world, it looks like this. So I'm going to fly, and I'm going to take another picture. And now I know at this specific coordinate on the Earth, that's what it looks like. And it's going to keep doing this. It's going to keep going across the mountains and the forest and the fake ocean and everything. And you're going to end up, when you put this into a GIS software, GIS meaning Geographic Information System software, you're going to get you're going to know where the center of these pictures, you're going to know the GPS coordinate, you're going to know what it looks like, and then now we can create, there's mountains here, there's trees here, this is ocean. Now you're going to get an understanding of what the Earth looks like from the fact that you knew where you were. You didn't know what it looked like. You made sensor observations. You fused that with the fact that you knew where your location was, and now you can map. So this is how mapping works. But that's not really the problem we've given you, is it? So the problem we've given you, unfortunately, is the fact that you have no idea where you are, and you have no idea what the environment looks like. And the problem is my Xbox controller doesn't work. The problem is, to localize, you need to know what your environment looks like. And to map, you need to know where you are. So now we have Now the problem we currently have is this is a chicken and that's an egg. What do I do? SLAM! SLAM is the best thing since things were things. The other best thing. I need to erase my board. Give me like 30 seconds. Okay. SLAM stands for Simultaneous Localization and Mapping, and it's probably about the only acronym in the world that actually makes sense. It does exactly what it says. It simultaneously localizes and maps. And the reason this is fantastic is because before this happened, there was really no way in the robotics industry to like localize in unknown environments because of the same chicken and the egg problem. Okay, so now for the next 20 minutes, what I'm going to attempt to do is explain to you how to localize and map at the same time. If at any point I lose you, please let me know. Because if you don't get step 1, you aren't going to get step 2. And if you don't get step 2, you aren't going to get step 3. Cool? Okay. So, what SLAM attempts to do is it says, this is confused robot. Confused robot is confused because he has no idea where he is and he has no idea what is around him. So he's sad. We want to make confused robot happy. Now, I will preface this by saying the SLAM that we are going to go through is called Lidarbased SLAM with odometry. And that's a lot of words. Basically what that means is your main sensor that we're using for SLAM is a LiDAR. And odometry in 3 seconds is... Did Juan talk to you guys about wheel encoders yesterday? Yes? No? Little bit?
Yeah.
Cool. Okay, so a wheel encoder is basically... They're on your wheels, your motors have encoders, and they tell you when you're running it how many times your wheel has spun or something like that. And based on that, I'm going to draw this here. So this is one wheel, this is another wheel. Not everybody can see this. This is one wheel, this is another wheel. If I know how many times this wheel has spun and I know how many times this wheel has spun, I can say, okay, if my robot was here, I know how many times each of these wheels have spun. I basically, after some math, I end up with an R and a theta estimate of where I am now with respect to where I was before because I know how many times my wheel has spun. And I think in this case you also need to know the diameter of your wheel. So the problem is we can't just use odometry to determine our position even if we knew what our position was here. Like if we assume we knew what our position was, I can't just use odometry to determine my new position because of the fact that wheel encoders are crap. Like they're terrible. They're so bad. Like the odometry estimate you get from here is it's bad. We won't get into how bad it is, but it's like it's not accurate to any degree in which we could actually determine the real location of the robot, because the first error might not be so high, but the second error will be squared, and then the third error will be cubed, and your error just grows and grows and grows until your robot is here and the estimate says it's 6 miles that way, and it's just not useful. So Yes, so SLAM that we're going through right now is SLAM with odometry. You still need odometry for SLAM, and I'm about to explain why. Okay. So here's confused robot, or confused robot. We're going to put it in this room. The room kind of looks like this. I think I have some better diagrams on the board because I don't trust my drawing ability. Yeah, okay. Pretend this room is the same as that room. So between us, we know what this room looks like. The robot doesn't know what the room looks like, so it's lost. So what SLAM does is the first thing it's going to try to do is it's going to take, at time t equals 0, time step t equals 0, we're in discrete time, by the way. It's going to take a LiDAR scan of the room. And it's going to say, okay, this is what I see, point cloud-wise. Right? The first thing SLAM is going to do, in localization and mapping, you always need an origin, right? You always need a reference point that you're going to measure everything with respect to. And SLAM, the first thing it does, it says, okay, the location of my LiDAR and my first scan is my origin for the rest of time. That's not going to change. The location of the LiDAR and my first scan is the origin. The positive x-axis is the direction that the LiDAR is pointing. Positive y is this way, and z-axis is out of the page. I would also like to make the distinction that this is two-dimensional SLAM. You can have three-dimensional SLAM. Once you understand 2D SLAM, 3D SLAM is very similar. The only thing is there's more landmarks and more data and more complicated point clouds. But yes, so first thing that happens, LiDAR scans the room, you generate a point cloud, and you generate an origin. Okay. The next step that happens is called landmark recognition, or more commonly, landmark feature extraction. So this is a pretty critical SLAM step. All of these steps are critical, but this one is probably, actually we won't say that. Anyway, this is a pretty critical SLAM step. Basically, what SLAM is going to do in the end is, the problem with unknown environments is they're unpredictable, right? I could have a person walk through my environment, the sensor will pick that up. I could have, I don't know what my walls look like and so on. And to localize, you need to first have some hard landmarks to figure out where you are. And these landmarks can't move around. Like, if I know where I am now and I see a landmark, I'm going to use this chair as my landmark. If I move, I re-observe that landmark there. Based on how I'm observing this landmark, I can determine my new position, right? So now the landmark moved from here, I'm now seeing it over here. I know I went this way. But if that landmark also moves, like if I see it here, the landmark moves there, I haven't moved, but I think I've moved backwards because I assume I'm referencing my position with respect to a landmark. Does that make sense? Okay. So SLAM not only has to recognize landmarks, number one, because you need to be able to recognize something as a landmark. It also needs to be able to determine which landmarks are good to use for localization. Because if I'm a robot in a room, a wall is a great landmark, but like Eric isn't, because he moves. That's Eric. Yeah. So before we get to like how SLAM determines what landmarks are good and not, the first thing that happens is we need to figure out what our landmarks even are. So this is the step of feature extraction. And I'm just going to do this with walls for now because like it gets hairy when you have like tables and chairs and people. But like if this is my scan, what it's first going to do is, so there's many ways to do this. The way I'm going to describe is called line creation midpoint extraction or something like that. Basically what it's going to do is it's going to look at the scan and it's going to do best fit lines all over. Because remember, this is a point cloud. There are no walls. These are just points in space. So the first thing it's going to do is say like, okay, these points look like they form a line. So I'm going to make that a line. These points look like they form a line. So I'm going to make that a line. And now what I'm going to do is I'm going to take a midpoint of this line. And I know the position of this midpoint with respect to the origin, which is the LiDAR. Remember, all we've done so far is look at the LiDAR scan. We have done nothing. Everything that we have got so far comes from that LiDAR scan, right? So now what happens, it does this for all of the walls. I'm going to assume there are only walls in this scan for a moment. Actually, you know what? Let's put Eric right here. Let's just assume Eric is in the scan as well. This is Eric. Eric is a point. There's also point feature extraction, or works very similarly to the line linear extraction, except for the fact that you don't need to determine if it's a line or not because it's just one point. So I have all of these landmarks. I have their positions with respect to the origin, right? And this just comes from the first scan. We haven't done anything besides take one LiDAR scan. Yes. Okay. So this is called feature extraction. We take the LiDAR scan, we look at what our landmarks are, and we don't even determine right now, are they good landmarks? Are they, like, that comes way later. These are our landmarks. I see these. And that's our first step to determining what our environment looks like, right? The other point I was going to make is the landmark here is not the wall. And this specific type of SLAM, which is line, midpoint, extra, whatever I said, the midpoint of the line is the landmark. Why that matters is because it like your implementation changes based on if your landmark is a point or a line or whatever it happens to be, because of the next step. The robot moves. Yes, sounds like kind of an irresponsible thing to do. You have no idea where you are, but you're going to move anyway. But that's exactly what it does. So here was the robot, here is the robot. And before we even generate the point cloud, actually, so not that this slide is wrong, we do create a laser scan, but before we generate the point cloud, what SLAM is going to now do is say, here's where odometry comes in. I measured some odometry while moving, right? Or I gave it a control input, a known control input, and based on this known control input, knowing some parameters about the robot or whatever, how much time do I have? Okay. We're going to move a little faster. I know my R and my theta, right? I have an estimate. I moved this far probably, right? From odometry. Now what SLAM is going to do is SLAM is going to estimate the position of the landmarks it expects based on the odometry that it measured. Does that make sense? Cool. Okay. So if my robot moved here, I think it moved here. Remember, odometry is terribly inaccurate, so this is an estimate. I think I moved there. This landmark is probably here. 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 This landmark is probably here, right? That's where I expect these landmarks to be. Then what it's going to do is it's going to generate the new scan. It's going to scan match again. Oh, sorry, not scan match. It's going to landmark extract again. And then it's going to say, like, okay, here are actually the positions of my landmarks. Here are where I predicted them to be. I believe purple is predicted. Purple is predicted. Blue is actual. So that's the actual position of my landmark. And now what it's going to do is compare. I thought it was going to be here, but it's actually here. Right? Oh, wait, no, sorry. Blue is original landmark. Green is new actual position. Purple is predicted. Does that make sense? And now you get a fused estimate for, it basically takes minimum error again, fused estimate between here is, so it doesn't just say, okay, this is where the new location of the robot is. And it doesn't just say, here's where the new location of the landmark is from the measured scan. It finds a happy medium in between the odometry estimate and the new scan estimate to generate the new estimated robot position with respect to the original LiDAR origin. Does that make sense? Okay. Yeah, so this is a lot.
How does it find the happy medium? Is it just like
30 seconds. We're going there right now. Yes, math. Yeah, so how does it find the happy medium? It does some math. And for the sake of time and for the sake of the fact that I don't fully understand the math either, because it's very complicated, I'm going to give you a very brief overview of how this does this. Also because Eric is about to tell you in about 15 minutes that no, we're not expecting you to implement this from scratch. I don't think any of us have implemented it from scratch either. There's a great library online called Hector SLAM that we're going to give you. But we did want you to understand it, what was going on first, so when you see things happening in SLAM, you know where it came from. So, in a nutshell, here is what's happening. I have this landmark, this landmark, this landmark, this landmark, this landmark. This is my original origin. This is my estimated robot position at like some current time t equals t greater than 0. And this is Eric, who is annoyingly moving back and forth in the corner over there. So I have these landmarks, right? So there's a couple of, so SLAM is just like 5 giant matrices that keep changing and keep getting bigger and then keep getting bigger and then keep changing. Like you have something like, at the end of SLAM, you have like a 1,000,000 by 1,000,000 dimensional matrix of just covariances, but we'll get there in a second. So I have all these landmarks. The first matrix I have in SLAM is P, that's my position matrix. My position matrix does literally exactly what it sounds like. It stores all of my positions. It stores the position of my origin, which is 0, 0. It stores the position of this landmark, stores the position of this landmark, stores the position of this, that, and unfortunately Eric as well. I will tell you why that's unfortunate in a minute. Yeah, so that's the first, is a position matrix. The second matrix is the core of SLAM, and this is the reason SLAM works. It's called the Covariance Matrix. I think it's Q. I don't know how they refer to it anymore, but it's the Covariance Matrix. It also, again, does exactly what it sounds like. It stores all the covariances, but the question is, what covariance? What is covariance? The Covariance Matrix takes every single landmark at every single time step and every single position at every single time step, and it calculates the covariance between the robot's position and that landmark and every other landmark, and that landmark and itself. So, and what a covariance basically is it tells you how useful, how related are these variables, right? So it'll say like, how related is this position to this position? How related is this position to this position? How related is this position to this position? How related is it to everything else? Which is why, as you can probably see now, these matrices get huge, because when you have more than 3 landmarks, like, it's a lot of covariances, because it's the covariance with respect to itself and everything else in the environment. So why does this matter? Because now what it's going to do is say, okay, let's calculate the covariance of the robot's position with respect to Eric, who is constantly moving back and forth. The robot is going to notice, or SLAM is going to notice, that the position estimate that I give for the robot has absolutely no correlation whatsoever with Eric's position, because Eric is bouncing off of every single wall. He's all over the place. So let's just, for, I don't even know what the symbol for covariance is, but let's say it's 0.1. It's something low. But it is going to say, okay, Noah over there is a fantastic landmark because he's just sitting there. And he's not bouncing over the wall. So my covariance with respect to Noah is actually 0.75. And then after some point, if like after 7 time steps, let's say my covariance with respect to Eric's position is still 0.1, we're just going to get rid of Eric. Sorry, Eric. Because SLAM is going to say, hey, there's absolutely no point in me measuring my position with respect to Eric if he is going to be all over the place and it doesn't tell me anything about where I am. But if Noah keeps sitting there, we're going to keep Noah because he's a great landmark. Now let's say Noah gets up for like 25 time steps. Noah's a great landmark. Let's say Noah gets up and starts moving around. The covariance is not going to immediately drop because at this point we trust Noah. He's a good landmark. He's been a great landmark for 25 time steps. So at time step 2, it's going to be like, okay, let's say my covariance is actually 0.6 now, because the reason it drops, though, is I have all of these other also pretty good landmarks, walls, so on and so forth. And it's going to say, okay, I trusted Noah, but these also really good landmarks are also telling me, well, I really should be here, but Noah's moving and telling me I should be here. So maybe I should trust Noah a little less because I have 5 landmarks that are telling me I should be here, right? You still will get error in this estimate. You're like, because of the fact that we still highly trust Noah, you'll still get some error in this estimate. But time step 2 times after Noah starts moving, you're going to be like, oh yeah, let's get rid of Noah. Bye, Noah, because he's moving. It does not take SLAM very long to realize which landmarks are crap. It takes it about 2 or 3 time steps. So this is how SLAM determines. This is how SLAM gives you an estimate. The only other thing I was going to mention is the map itself. How map generation works is it literally takes the scan, and after a couple time steps, when it's trusted the scan, it just says, okay, here's my map, because your scan is your map. Now, this gets to the point later, like, what if, the point was made earlier, like, okay, if my room looks like this, and my LiDAR is here, my LiDAR can't see that region of the room, right? So how does SLAM map that part of the room? This is why it's called simultaneous localization and mapping. Basically what you do is you keep mapping as you go. You understand, like this, what this is gonna do is, let's say the robot moves like this, for example. What the SLAM maps are gonna look like is it's gonna start like this. These are defined walls. This is actually going to be part of the map down here. Here's where the robot is. This is a defined hard part of the map. These lines are going to be black. This will be a gray background. You know exactly what's going on here. You'll get some fuzz around here at the edges because it can't see this part yet, but it knows there's going to be something there. It sees an opening. It doesn't see a wall. It sees an opening. And then it's going to be like, then when it moves here, it's going to look something like this, with some fuzz. And then it's going to look something when it moves to its last position. This is not even, that's a terrible drawing, but then it's going to finally end up looking like that. As you move, it updates the map. Real quick, I want to talk about an interesting limitation we found with Hector SLAM. This will take me probably 2 minutes. So when we were trying Hector SLAM, the SLAM we're giving you, Hector SLAM, the only difference between Hector SLAM and the SLAM I just explained, the SLAM I just explained uses wheel encoder odometry. The SLAM that we're giving you, Hector SLAM, uses what's called scan matching odometry. And scan matching odometry, the only difference is it takes this laser scan and it takes the time step t+1 laser scan. It tries to match them. And it says, okay, my origin on this laser scan was here. My origin on this laser scan was here. Because remember, the location of the LiDAR is the origin of the laser scan. And then when it matches this, it says, okay, that's how far I've moved. That's my odometry estimate. The reason this works is because LiDAR is actually pretty good as far as point clouds go. So that's the only difference. But anyway, so the first time we turned on SLAM here, this was like, we literally made a pentagon and we put a LiDAR in the middle of it and ran SLAM and saw what was going to happen. This is the first map we got. And then we were like, okay. John was like, well, what if we just screw with it and put a cardboard wall in the middle of the room? So that's exactly what we did. We put a cardboard wall here and we didn't move the LiDAR. And it turns out the map we got was this. There was no wall in this map, and we were like, what the heck? We've put a wall there. And so the reason this happens is because, and the reason I'm pointing this out is because you might see this with scan matching odometry because you're using scan matching odometry. Scan matching odometry has one big problem, and the big problem with scan matching odometry is the fact that it assumes your scan will not significantly change from time step to time step. And the reason it has to assume that is because it needs to match the scans, and to match the scan, your scan can't significantly change. So when we gave it this giant wall here, the scan now looks like this. And it's trying to match this to this, and it freaks out. It has no idea what to do. So it just was like, okay, that scan is fake news. It can't be real. So it just goes back to this estimate. And it actually just keeps doing this. Like, it just, for no matter how long we left the LiDAR there, the map didn't change. It refused to believe we put a wall there. Until we started moving the LiDAR around back and forth, and then it was like, oh, okay, maybe there's a wall there, and it finally put a wall here. So this is probably not something you'll run into during the competition because we're not gonna stick a wall in the middle of the field. But if you see some weird things, this could be one reason. Yeah. I think that's all I have for you. Yes, Eric has homework for you, the end.
So I think we'll take a 5-minute break if you guys want to get coffee or something. And then start next. So we'll be back around 11, 12.